Okay, welcome to part 2 of this video preparation. Now we're going to talk about probably the meatiest, most complicated part. We'll try to do it in a fairly short but organized way. This is several topics we'll talk about. We'll talk about the central limit theorem and the distribution of sample means. And really we're talking about the theoretical basis of the idea of the standard error of the mean. And we'll talk about essentially the purpose of the standard error of the mean is to estimate the population mean from the sample data to give you a range estimate. And really we're talking about how to calculate confidence intervals. And so we'll try to march into all of that right now. Excuse me. So again, I think I've said this before, the real point of statistics, at least one of the real points, is that you have sample from a data from a population. You don't have a population. You almost invariably have a sample, and you try to calculate or estimate information about the population from your mean and standard deviation. So you calculate the mean and standard deviation for your sample, and you want to estimate the mean and standard deviation of the population. We said before, when you estimate the standard deviation of the population from the sample, you use the n-1. You'd be a little conservative because you don't really know the full standard deviation of the population. When you want to estimate the mean, if you want to make a point estimate, just a single estimate from a population, your best estimate invariably is the mean of the population. If the data is from a normally distributed data, if it's from an interval scale of measurement, your sample hopefully is representative, and if you have to make a single best guess, it's the mean of that sample. The problem is, you know that that's probably not 100% likely to be correct, and so really you want to make a range estimate that gives you some more confidence, if you will. And that's where this phrase confidence interval comes from, because a confidence interval is simply a range of values centered around the sample mean and calculated using the sample variability that is X%, 95%, 99% likely to include the mean of the population from which the sample was drawn. So again, all you're doing, you're taking your data from a sample and say, well, if I have to guess the mean of the population, I'm going to guess the mean of my sample. But if I'm going to give myself a little more coverage, if you will, I'll create a range that I think the mean of the sample is truly in, and it'll be centered around the sample of the mean. It'll be centered around the mean of the sample, but it will be a range that's based upon the variability of that sample data, and we'll show you how that comes from. So a confidence interval, 95% confidence interval, is a range of values centered around the sample mean, calculated using the sample variability that is 95% likely to include the mean from which the sample was drawn. So how do you calculate it? Well, we'll give you the long version and then the short version. The long version is the theoretical basis. It's relevant, but it's not the only important part. So let's consider a hypothetical situation. You've got a big population of numbers. You don't know the population mean, but you're going to be asked to guess what it is. Before you guess, you get to do the following. You draw a bunch of samples of maybe 120 each, kind of a thing. Then you calculate the mean of each of those samples. So you pulled a bunch of samples, and now you have mean values, not individual values within the sample. You have sample means. Then you plot the distribution of sample means. Well, if you have a big enough distribution of sample means, what do those sample means look like? According to the central limit theorem, when multiple samples are drawn from a population, you get a normal curve. This is by definition the distribution of sample means. And this is a classic normal curve. This is from reading scores from an example from a textbook, but basically it's a normal curve. And this is a situation where you had multiple huge samples drawn. And the mean of all those samples is 70. One standard deviation goes up to, the standard deviation is 3, so it goes up to 73. One standard deviation below goes down to 67, and so forth. If it's a normal curve, what do we know about it? We know that 34.13% of the data, the sample means, are found between the grand mean of 70 and 1 standard deviation above the mean. Similarly, we know that 34.13% of the data is between the grand mean of 70 and 1 standard deviation below, 67.60. That's just because it's a normal curve. And again, we get another 13.6% if we go a standard deviation above, a second standard deviation, and get another 13.6 if we go a second standard deviation below. That's because it's a normal curve. And the central limit theorem says that if you draw sample means from a large population, the distribution of sample means will be a normal curve. Again, going back to estimating the population mean, if we're going to make a single point estimate of the population mean, we have this data, we're going to say, well, our best bet is still that the population mean is 70. We don't know. That's just the mean of our distribution of sample means. But what if we want to be more certain, a little more confident? That's where we get the confidence intervals coming into play. And here's the fact, and this is the fact that's kind of confusing, but it's the fact and it's a realization. The standard deviation of the distribution of sample means, that is 1 standard deviation to the right or standard deviation to the left, drawn from a population, is by definition the standard error of the mean for the population from which the samples were drawn. So the standard deviation of this hypothetical distribution of sample means is essentially the standard error of the mean. That's by definition. So according to the central limit theorem, and this may sound confusing, but because you probably learned that the standard deviation divided by the square root of n is equal to the standard error of the mean, and that's true in a very limited kind of a sense. But in the theoretical sense, the standard deviation of the distribution of sample means, which is a hypothetical thing that you'll never calculate, is by definition the standard error of the mean. And so if you move 1 standard deviation unit on this curve to the right and also to the left, you will capture 68.26% of the sample means. So if you say the range between 67 and 73 is a range estimate of where I think the population mean is, you are 68.2% likely to actually capture the true population mean. And so that would essentially be, by definition, the 68.26% confidence interval. Well, nobody actually uses that number, but that's what that would be. Because this is a normal curve, and we know that 1 standard deviation to the right, 1 standard deviation to the left will capture 34.13% of the data on each side. And since this is the distribution of sample means, you are 68.2% likely to capture the true population mean if you go from 67 to 73, because that's 1 standard deviation unit, or 1 standard error of the mean in this case, because it's the distribution of sample means. It's 1 standard deviation unit to the right and 1 to the left. And so you would say it's between 67 and 73, plus or minus 1 standard error of the mean on this distribution, is 68.26% likely to capture the population mean. If you go 2 standard deviations, you go 1 and 2 to the right, 1 and 2 to the left. Now you're going to catch your 47.75, I think it was here, and 47.75 here. Between those two values, plus 2 and minus 2, you're going to capture 95.5% likely to capture the true population mean. So you would call that the 95.5% confidence interval. Nobody reports that. What do they report? They report a 95% confidence interval. So this is a 95.5% confidence interval from 2 standard deviations below to 2 standard deviations above. When people don't like that, that's not very pleasing. It's kind of a funky number. So what do they usually calculate? The 95% confidence interval. Again, think of 1.96. If 2 full standard deviations is 95.5%, 1.96 of those standard deviation units is going to capture 95% of your sample means. So the range between 1.96 standard deviation units below the mean, 1.96 standard deviation units above the mean, that is 95% likely to capture the true population mean. And that 1.96 comes from our normal curve and the z-table that we talked about previously. And if you work out the math, if the standard error of the mean here is, the standard deviation here is 3, 1.96 times that, you end up with a range from just slightly above 64, 64.12, to just slightly below 76, 75.88. That is your 95% confidence interval. That range, centered around this mean of the distribution of sample means, is 95% likely to capture the true mean of the population. You never knew the mean of the population. In this situation, you took multiple large samples. You plotted a distribution of sample means. From that, you created this curve. This curve, the distribution of sample means, the average was 70. The standard deviation was 3. If you go 1.96 standard deviation units on either side, you're going to have 95% of the data. That is what a 95% confidence interval is. Now, before we back out of this entirely, I want to make one more thing absolutely clear. In this example, and only in this example, with the distribution of sample means, I've used the term standard deviation, which is a 34.13% of the data from the mean to one standard deviation above the mean. That is, by definition, the standard error of the mean only for the distribution of sample means. And the reality is, you never calculate the distribution of sample means. Nobody in their real world, when they analyze data, say, I have a sample, I want to figure out something about the population, so what I'm going to do is I'm going to take hundreds upon hundreds of additional samples from that population, and I'm going to plot a distribution of sample means, and from that distribution of sample means I'll get a standard deviation, and that will be my standard error of the mean value. It is only the case that the standard error of the mean is, by definition, one standard deviation in this hypothetical distribution of sample means. We have this discussion here so that you understand the relationship between the term standard error of the mean and the standard deviation. The standard error of the mean is, by definition, one standard deviation in the hypothetical distribution of sample means that in reality nobody ever makes. But it's not as if the standard error of the mean is some never ever used kind of a value. It is used. And so now we'll try to get to, when we talk about the standard error of the mean in the real world, what are we getting at? One of the things we're getting at is we're trying to estimate, if you had taken hundreds upon hundreds of samples, one standard deviation unit here would be the standard error of the mean. Now we're going to try to define, we're going to try to show you how you mathematically can get there. Before we do that, let's just try to wrap this up. So the 95% confidence interval is basically the range between 1.96 standard errors, or standard deviations in this curve, above the mean and below the mean. And so it's between 64.12 and 75.88. You can say that you're 95% likely that the mean of the population, which you never calculated the mean of the population, but you're 95% certain that the mean of the population is between this value and that value. And that, in this example, is based upon multiple samples and a plotted distribution of sample means, which is a normal curve, and in this case the standard deviation in this normal curve is, by definition, the standard error of the mean. So the 95% confidence interval is a range of values centered around the sample mean that is 95% likely to include the true population mean, even if you never know the population mean, and you calculate using the standard error of the mean. because the standard error of the mean is by definition one standard deviation unit in this function. But it's always going to be, so a little foreshadowing, if you will. When we calculate a confidence interval, and if you've seen one calculated before, it's always based upon the standard error of the mean. And so in the hypothetical situation we just walked through, you do multiple samples, and you create a curve, and you get a standard deviation. That's by definition the standard of the mean. In the real world, though, you shortcut a lot of that, and you calculate a standard deviation of a sample, and from that you will estimate the standard error of the mean. And from that estimated standard error, you will calculate a confidence interval. We'll get to that in just 1 second here. So there are really two approaches for calculating or estimating the standard error of the mean. The one we walked through for the past 5 minutes is sort of the never land approach. It's the theoretical basis of the term standard error of the mean, but you don't actually do this. But if we took a huge population of data, and we took hundreds and thousands of samples of 120 or more, and we'll talk about the significance of the sample size in a minute, and from that you calculate the sample mean of this distribution of sample means. That's your single best point estimate. But then you want to give a range estimate, so you need the standard error. But if this is a distribution of sample means, one standard deviation is by definition the standard error of the mean for that population. So then you'd simply go 1.96 this way, 1.96 that way, and the distance between those two is the 95% confidence interval. Again, that's kind of a never land approach. You don't really use that. Here's what you really do. You don't calculate the standard error of the mean, you estimate the standard error of the mean with a calculation. But it's still an estimate. This is the real world. If you've seen stats and you've seen a standard error of the mean calculated, you say, oh, I get that part now. You take a relatively large sample, you calculate the standard deviation of the sample using normal procedures. Again, variance is the sum of the squared deviations from the sample mean, that quantity divided by n minus 1, because we call it a sample, so we use n minus 1. Once we have the variance, then we calculate the standard deviation. That is by definition the square root of the variance. So now we have the variance and the standard deviation of a single sample. From that standard deviation of the sample, you can estimate the standard error of the mean by using the formula standard error of the mean is the standard deviation divided by the square root of n. So if it's only from a single sample, the standard deviation is equal to, the standard error of the mean is equal to the standard deviation divided by the square root of n. And you've probably seen that in the stats book all the time. What you're doing with all of that is you are basically estimating that other value of the standard error of the mean, which you never calculate really, which is that hypothetically derived standard deviation of the distribution of sample means, which is in fact the standard error. So which would you choose? You can't really choose, because nobody's going to sit around and say, well, I have a population I'm interested in, so I'm going to take hundreds and thousands of samples. No, people don't do that. They take method number 2. But it's only an estimate then, because you really don't know unless you take these hundreds of thousands of samples. But practically speaking, method number 1 is not an option. So really, when you're talking about in the real world, in statistical calculations, all the standard error mean values, which are calculated from the standard deviation and the sample size, always are only an estimate of the standard deviation of the hypothetical distribution of sample means. That's what you would get if you were to make multiple samples of many large samples from a very large population. But you're simply making that calculation based upon the standard deviation divided by the square root of n from a single sample. So we've covered a couple different aspects of it, so let's talk about standard error of the mean briefly. So in its most elementary sense, the mathematical statement is really straightforward. The standard error of the mean is equivalent to the standard deviation from a single sample divided by the square root of the sample size. SEM equals SQ divided by the square root of n. SD divided by the square root of n. People have done that, and you probably have seen that in text, and that's what most people do, and that's what is often thought of as what people are doing. That is to say, step 1, calculate the sample, the standard deviation of the sample. And remember to use the n-1 because it is a sample. So calculate the variance, take the square root of the variance, that's the standard deviation. Divide the standard deviation value by the square root of n, and that is the standard error of the mean for that sample, which is an estimate of the standard error of the mean if you were to make this hypothetical distribution of sample means. And essentially what the math is pretty straightforward. It's easy peasy. What can you do with the standard error of the mean calculated from a standard deviation? You can report a mean and a standard error in your article, which I wouldn't recommend, or you can calculate a confidence interval to predict the population mean, which is the true use, legitimate use of the standard error of the mean value. The standard error of the mean that is calculated from a sample is really used primarily and exclusively as a way to create a range estimate for the mean of the population from which that sample was drawn. To put another way, the standard error of the mean is legally used to calculate a confidence interval, but it is illegal when it's used as a measure of dispersion or variability of the data. So that's the most practical, most elementary. It's encountered often in an illegal sense. That is to say that very often the data are summarized in a table as mean and standard error of the mean, and people try to use that as a way to depict the variability or dispersion of the data, as if it's the standard deviation or the variance or something like that. The truth is the standard error of the mean is not supposed to be used as a measure of variability. It is used primarily as a way to estimate provide a range-based estimate of central tendency, a confidence interval. The most esoteric or theoretical use is what we said before. If you've got this enormous population, you take an enormous number of large samples and you plot a distribution of sample means, then in reality, one standard deviation on that hypothetical population is by definition the standard error of the mean of that population. And then the hybridized theoretical and practical is really, as I said before, using the standard error of the mean combined with the appropriate t-distribution to calculate and report confidence intervals. We'll get to the t-distribution part in the third video. So here's the real point. We're trying to pull out of this a little bit. You have a sample from a population. You can calculate a mean and standard deviation for your sample. If you want to estimate the mean of the population from which you drew the sample, your single best point estimate is the mean of the sample. But if you want to give a range estimate of the sample, you'll calculate a confidence interval. From the confidence interval, you'll say, after you calculate it, the 95% confidence interval is the range of values centered around the sample mean and calculated using the sample variability that's 99% likely to include the mean of the population from which the sample was drawn. In the next video, we'll talk about the influence of sample size on calculating confidence intervals, because sample size does in fact matter. Again, just before we finish this up, to go beyond a single point estimate of the population mean, you need to do something that is a range that has a confidence statement. So that's a confidence interval. And it's going to be dependent upon the standard error of the mean, which you're going to estimate from your population from your sample standard deviation, and it will depend upon the sample size, which we'll derive from the t-distribution. So we'll talk about those in the next video.